What if the most advanced space telescope ever built has just forced scientists to rethink everything we know about the birth of the universe? What if something so ancient, so massive, and so luminous has been found that it shouldn't exist at all? At least, not according to the physics we thought we could trust. The James Webb Space Telescope, designed to peer further into the past than any instrument before it, has now uncovered galaxies from the universe's earliest days that challenge everything we know about how the cosmos began. And one of these, a record-breaking galaxy called MOM Ziad 14, is pushing us to the very edge of what we thought was possible. In this journey, we'll travel back over 13 billion years to explore Webb's record-shattering discoveries, examine why these galaxies break our models of cosmic evolution, and consider what this might mean for the Big Bang Theory itself. Halfway through, we'll uncover a surprising pattern that could rewrite the early chapters of the universe's history. And at the end, we'll ask the question no one can yet answer. Are we simply missing a few details, or is the universe hinting at something entirely new? When NASA, ESA, and the Canadian Space Agency launched the James Webb Space Telescope in December 2021, the world watched with a mix of excitement and anxiety. This was a mission more than 2 decades in the making, plagued by budget overruns, delays, and technical challenges. But if it worked, it promised to revolutionize our view of the cosmos. At a cost of nearly $10 billion, Webb had a lot riding on it. The telescope was designed to look further back in time than any observatory before it, capturing light that has traveled for more than 13 billion years. Its primary mission? To find the very first galaxies and stars, to see the so-called cosmic dawn when the universe lit up for the first time. For decades, the Hubble Space Telescope had been our workhorse in space, pushing the cosmic frontier back to roughly 400 million years after the Big Bang. Hubble's deep field images showed us a universe teeming with galaxies, each a collection of billions of stars. But it was limited by its instruments, which were tuned mainly for visible and ultraviolet light. Webb was built to see the invisible, infrared light. This is crucial because the universe has been expanding for 13.8 billion years, stretching the light from the earliest galaxies into longer, redder wavelengths, a phenomenon known as cosmological redshift. By observing in the infrared, Webb could detect the faint stretched light from objects that Hubble could never see. Infrared vision also meant Webb could peer through cosmic dust clouds that block visible light, revealing star-forming regions and the cores of distant galaxies. Its 6.5-meter segmented mirror, made of gold-coated beryllium, could collect far more light than Hubble's 2.4-meter mirror, making it both more sensitive and more powerful. Webb's 4 main instruments, NIRCam, NIRSpec, MIRI, and FGS/NIRIS, were designed to capture detailed images, measure spectra, and analyze the composition of some of the faintest, most distant objects in the universe. Not long after Webb began its science operations in mid-2022, the JWST Advanced Deep Extragalactic Survey, or JADES, delivered its first major shock. Astronomers identified a galaxy called JADESGSZ 140. This wasn't just another faint smudge in the deep sky. Careful analysis revealed that we were seeing it as it appeared only 290 million years after the Big Bang, more than 13.4 billion years ago. This made it the most distant confirmed galaxy ever observed at the time. But it wasn't just the age that stunned scientists. JADE's GSZ 140 was massive, bright, and chemically evolved. Its light carried the fingerprints of oxygen, a heavier element that can only be created inside stars. This meant that multiple generations of stars had already lived and died, enriching the galaxy's gas with heavier elements, all in an incredibly short cosmic timespan. This discovery alone was enough to raise eyebrows. Our standard models of galaxy formation suggested that it should take hundreds of millions of years to build galaxies of this size and complexity. Yet here was one, fully formed, less than 300 million years after the universe began. But before astronomers could fully digest this, Webb found something even more remarkable. Enter MOMES 14. This galaxy was observed as it existed just 280 million years after the Big Bang, pushing the record even closer to the very beginning. At first glance, 10 million years earlier might not seem like a big difference. But in the infant universe, this was a huge leap backward in time, into an era when the first light from the earliest stars had only just begun piercing through the hydrogen fog left over from the Big Bang. This period, known as reionization, was when ultraviolet light from young stars began ionizing the surrounding hydrogen, making the universe transparent to light. Finding a fully formed, massive galaxy in this era is like walking into a room of newborn infants and finding a fully grown adult. It simply doesn't match our timeline. The problem becomes clearer when you consider how galaxies are thought to form. After the Big Bang, the universe was hot, dense, and almost entirely composed of hydrogen and helium. Gravity slowly pulled gas together into the first stars, which lived fast and died young, exploding as supernovae and seeding their surroundings with heavier elements like carbon and oxygen. Over hundreds of millions of years, small clumps of stars merged into larger structures, eventually forming the massive galaxies we see today. This process is slow, messy, and inefficient, but JD's GSZ 14-0 and MOMSA 14 appear to have done it all at breakneck speed. How could this be? Astronomers have proposed several possible explanations. One is that dark matter, the mysterious invisible substance that makes up about 85% of the matter in the universe, played a more aggressive role in the early cosmos. Massive dark matter halos could have pulled in gas at astonishing rates, triggering intense bursts of star formation much earlier than we thought possible. Another idea is that galactic mergers were more frequent in the young universe, allowing small protogalaxies to combine rapidly and build up mass far faster than in the present day. There's also the possibility of population 3 stars, the very first generation of stars made almost entirely of hydrogen and helium. These stars are thought to have been far more massive and luminous than modern stars, burning through their fuel quickly and producing heavy elements in a fraction of the time. Yet even with these ideas, the sheer number of such early massive galaxies is surprising. Webb isn't just finding 1 or 2 anomalies. Surveys are revealing dozens of these objects from the same early period. This suggests that the early universe was much more crowded and structured than we previously imagined. If true, it could mean that the so-called cosmic dawn began earlier and evolved faster than standard cosmology predicts. The implications are far-reaching. It could shift the timing of reionization, change our understanding of how quickly black holes grow, and force us to reconsider the role of dark matter in galaxy formation. It might even hint at new physics that we haven't yet discovered. One of Webb's most iconic images, the Deep Field view, illustrates this beautifully. In a tiny patch of sky, no larger than a grain of sand held at arm's length, Webb reveals thousands of galaxies, many of them from the universe's first billion years. The faintest, reddest smudges are candidates for being among the earliest galaxies ever formed. The sheer abundance of them suggests that star and galaxy formation in the early universe was not an isolated, gradual process. It was a rapid, large-scale transformation. Does this mean the Big Bang theory is wrong? Not at all. The evidence for the universe's expansion and its hot, dense beginnings remains overwhelming. But it does mean that the details of what happened after the Big Bang and how quickly complexity arose may be more complicated than we thought. If galaxies like MOMSA 14 were already massive and evolved just 280 million years after the Big Bang, then our cosmic timeline needs adjusting. The simulations we use to model the early universe will have to account for more rapid star formation, earlier chemical enrichment, and more efficient matter assembly. Looking ahead, Webb's discoveries are only the beginning. As it continues to scan the skies, it will collect more data on these early galaxies, measure their chemical compositions in greater detail, and perhaps find even earlier structures, maybe as early as 200 million years after the Big Bang. If that happens, it would force a major rethink of how quickly matter organized itself and challenge our assumptions about the first stars and galaxies. The early universe, as revealed by Webb, was not the quiet, empty place we once imagined. It was dynamic, crowded, and producing enormous structures at breakneck speed. Whether the explanation lies in faster star formation, unusual dark matter behavior, or entirely new physics, the James Webb Space Telescope has opened a window to a richer, more complex cosmic dawn than we ever dared to imagine. So, what do you think? Are we just fine-tuning our cosmic models? Or are these discoveries the first hints that something much deeper and stranger is going on? The James Webb Space Telescope is only getting started, and the universe still has many secrets to reveal.